Second rule is that if you want a break, just ask for it. Don't worry if it's going to disrupt the flow. I just want every single person to focus. And rule 3, if the lunch comes, I don't want to hear my name. It's a joke. It's not literal. It's fine if you want to ask a question during the lunch break. This lecture depends on your understanding of p-value. Remember, who can define p-value? Just a quick little refresher. P-value. Ask me to turn the scene question. Okay, yes?
So if your p-value is less than 0.05, then your null hypothesis is true. Your null hypothesis, you reject the null hypothesis and you accept your hypothesis.
Yes, that's true. What you said is true. What is p-value? It's a probability.
Yes.
Right? It's a probability. It's a probability of getting a certain result, or more extreme than that result, given that the null hypothesis is true. Okay? Now this is a mouthful, but we all need to understand this again. Basically, let's just take a quick example. Let's say we have this distribution, and this is 0, and everything past here is going, more positive. Everything here is going more negative. What's the chance that you get, for example, from this, you get a specific sample, and the mean of that sample is 0 or more? What's the chance? What do you think? And I want this whole area. What do you think it's going to be? 50%, right? So it's like tossing a coin. For you to get 0 or more, it's like tossing a coin. And it makes sense because that's half the distribution. Now, why do they say, given the null hypothesis is true? It's because we want to see what's the chance of getting that particular thing with nothing affecting it. Okay? So the best way to explain this is by going back to Tea Lady. Remember Tea Lady? Robert Fisher attended this tea party, and he saw a lady who said, if you bring me 6 cups, 3, 4, 5, 6, and if you put sugar, or it was milk or something, with sugar then tea, or tea then sugar, and 3 of them, like 3 are one way and 3 are the other way, I will tell you exactly which 3 had the sugar first. I'll tell you exactly which 3 had the tea first. So Robert Fisher, being the man of numbers, you know what he said? He said, the chance, or the total number of different combinations is 20. There are 20 different ways we can put sugar and tea in this one, or we can put sugar first and tea and sugar. So we can arrange them in 20 different ways. And she could say them in 20 different ways, But there's only one way that's correct. There's only one combination that if she says it, that's correct. So what does he say? He says, let me calculate a p-value. So what was p-value again? The probability of getting a certain result, or more extreme than that result, given the null hypothesis, is true. So her p-value is 1. One result, because you can't get less than 1, This is integers. So 1 result out of 20 possible combinations, right? But why do we say given the null hypothesis is true? It's because of a very simple rule. Let's say she really can tell the difference, then her chance is not this. Let's say she can tell the difference 100% of the time. That means her chance is 20 out of 20. The only reason why p-value is not 20 out of 20 and it's 1 out of 20 is because of this last part that we say, given the null hypothesis is true. So what does it mean, given the null hypothesis is true? It means she got it absolutely by luck. Absolutely by luck. So if this chance of getting it by luck is 5% or less, that means we reject the null hypothesis. So here's what's going to happen. He calculated it is 1 out of 20 of her getting it purely by luck. But if she gets it, this is what he'll say. Okay, so she had a 5% chance of getting it. That's a pretty low chance. So what's the more logical conclusion? It's not really 5%. It's more, we don't know how much, but it's more than what we think it is. Because the null hypothesis is false. She really can tell the difference. Now whether it's 20 out of 20 or 19 out of 20 or 18 out of 20, it differs. It always differs. Okay? Does this make sense to everyone? It's really important that this makes sense. Okay?
Could you just repeat the last part?
We'll repeat the whole part. She's given 6 cups. 3 of them will have sugar first, then tea. 3 of them will have tea, then sugar. And we won't tell them which is which. We won't tell her which is which. So her job is just to taste it and then say which three have the tea and sugar in them, or tea, then sugar in them, and then automatically the other three have the sugar then tea. Okay? Robert Fisher calculated the total different combinations she could say, which was 20. But there's only one correct combination where she gets absolutely on the dot, absolutely correct, which is 1. So her chance of getting it correct purely by luck, given the null hypothesis is true, is 1 out of 20. Biostatisticians, they agreed, halas, 5% or less, if the probability of being lucky, if the probability of getting it by pure chance is 5% or less, reject the null hypothesis. Reject it. What do we mean? She didn't get it by luck. It means she got it fair and square. She got it because she actually can tell the difference. In other words, we are accepting our hypothesis, which is she really can tell the difference. Make sense? Does this make sense to everyone?
Yes.
This is a really important principle. Now we're going to take 2 examples. Our first example is about pregnancy. Okay? Pregnancy, let's say we have a specific pregnancy test. You know, the regular one that people, they just pee on it. Some of you may have seen this example. Oh. What do you usually expect when a male pisses on the thing? Will it be positive?
Negative.
It will usually be negative, right? So usually the correct decision, whatever happens, is that usually they're going to be negative. This is usually what happens, and this we trust it, right? If a female is not pregnant, what do we expect?
Negative.
Negative. So she's supposed to get a negative, right? What if a female gets a positive?
She's pregnant.
She's pregnant, right? So this. What if a male gets positive? Testicular cancer, but it's you can't say he's pregnant, right? You can't say it. So it's a mistake, right? So now we covered all of these 4 bases. Okay. Sometimes we make mistakes. Now a pregnancy test is a bad example because it's actually really accurate. But sometimes we make mistakes. Sometimes a woman is pregnant, but the pregnancy test says negative. She's pregnant, but the pregnancy test says negative. So it's a wrong negative, right? What's another way of saying a wrong negative? A false negative. Now false negative, look, let me just make it very clear here. Wrong negative, false negative, false negative, and beta, okay, and type 2 error, these all mean the same thing. All of them. So if I say a woman who's pregnant got a negative pregnancy test, that is a beta. We can say type 2 error. We can say wrong negative. You can say false negative. Now, no one really says wrong negative. They say false negative. They say, I'm just keeping this here to show you that you might hear sometimes I say beta, then once another second I say type 2 error. They all mean the same thing. What about a guy? A guy gets a positive pregnancy test. Is he pregnant?
No.
So it's a wrong positive. Wrong positive. So a wrong positive. Wrong positive. You can also say it's a false positive, right? Positive. We can also say it's called an alpha error. We can also say it's type 1 error. I'm not going to write type 1 in space. Because these all are basically, let's say female is pregnant. I lost my train of thought. The wrong positive is a male getting a positive pregnancy test. The wrong negative is a female who is pregnant getting a negative pregnancy test. So look, usually, we are here and here. We're making the correct decision. If a female is pregnant, she's getting a positive. Usually. If a male is pissing on the thing, he's gonna get negative. Okay? But sometimes we make mistakes. Sometimes mistakes happen. صح إنه it's unlikely, but they're possible. They happen. This was why in the previous crash course, remember when I told you, can a person be 60 feet tall?
No.
Hypothetically, yes. Can someone be as tall as Al-Faisaliya? It's unlikely, but it can happen. It's possible. Can someone piss on a pregnancy test, a male, and it shows him a positive? It can. So whenever I tell you, is it possible? I always want to hear you say yes. Because anything is possible. Absolutely anything is possible. Okay? If things like this were not possible, these errors, this one and this one, would not exist. But the reason they're positive, the reason they're possible, the reason they exist is because they're possible to happen. صح إنه they're unlikely, but it's possible for them to happen. Are we all clear on this? You're actually doing really well so far. What I don't want you to do is like the first batch that I taught and just forget all of this that I talked about as soon as we finish the lecture. Okay? So yeah, well, we're gonna start with our example. Okay? Water. Water, regular plain water. Does it make you smart? It keeps you alive, but does it make you smart? Now here's a really important concept. There's something called reality. And there's something called what the test tells us. So test. Sometimes they agree. Sometimes we do a test and we see that water really doesn't make you smart. Sometimes they agree in the opposite end. Let's say the reality of water is it really did make you smart. Sometimes the test will agree and it will show us that water is statistically significant and make you smarter. Sometimes they don't agree. That's where the mistakes happen. Sometimes water really doesn't work. It doesn't work. But the test tells us it does work. Sometimes the opposite happens. And what I just said was a type 1 error, the alpha error. Sometimes the opposite happens. The water really does make you smart. It really does work and it makes you smart. It makes you get 100% on all your exams. But the test tells us it doesn't. Type 2. This is a type 2 error. It's called beta. Okay? So let's take this example. I'm going to put down here two different things. So let's say, for example, water. I'm going to put this x. This x means it does not make you smart. Okay? It does not make you get 100% on all your exams. So this is our first thing. Our second thing, I don't know, what can we say? That's KitKat. KitKat, if you take it and you have a KitKat next to your during your exam day, if you take it right before your exam, let's say in truth, in reality, it doesn't make sense to say anything, just for the sake of the example, let's say it really does make you smart. Okay? Sometimes the test does different things. So let's just take a nice little example with normal distributions and try and understand what this means. This is the regular Al-Faisal population. Our average in our exams are usually 70. Give or take, depending on the exam. And the standard deviation, let's pick a number. Let's pick something easy. Let's say our standard deviation is 5, just for the sake of making it easy. So, 2 standard deviations, what will the value here be? I'll make it a bit further. It will be 80, right? So this, we can all agree, is 2 standard deviations, right? Now we can also do it backwards, because look, this is an important thing. We can also do it backwards, but in this case I'm not going to do it backwards, just for the sake of the example. You can never just assume that, for example, water will make you smart, or KitKat will make you smart. You always consider both sides. You always consider the fact that it could possibly make you worse, or make you score worse. In this example, and only this example alone, we will only consider one side, which is making you smart, just for the purpose of this example. Okay? So this is population. We didn't give them any medication, we didn't give them anything, we didn't do anything. Okay? We took a sample of 10 people, for example. So let's say we took 10 people, and their sample, their deviation, or their normal distribution was like this. Because it was exactly similar. I have to make it perfect, just 1 second. Okay. We gave them water. This was sample 1. Clear? Now I'm not going to show you the KitKat population yet. Just 1 second. We'll talk about this. Some of you may have already noticed it, right? Now, we're not going to do p-value and again, z and everything. No, we're just going to say, if we get a value past this mark, what do we say? Statistically significant, we reject the null hypothesis. If we get a value below this mark, what do we say? Statistically not significant, we accept the null hypothesis or we reject our hypothesis. Now, what is our hypothesis? It's that water makes you smart. That's our hypothesis. The null hypothesis says that, I'll just put this here, H0. We usually say null hypothesis is H0, okay? Alternate hypothesis, I didn't want to put 1, 0, so I'll put 0. So the null hypothesis is that the water does not work. Our hypothesis, H of 1, this is our hypothesis, or what we say also alternate hypothesis, it's that the water works. Okay? 95% of the time, since the water really doesn't work, you will get a mean here, 95% of the time. 95% of the time, you will get a mean that's here. In this case, our mean was here. Clear? 5% of the time, by chance alone, you'll get a sample maybe of Dean's List students, they'll get you a mean here. And what will you think? You will think the water works. Is that the case? Reality says the water does not work. Very, very important. This error, when you do it, it's called what? Type 1 error. We all agree? Because, so I'm going to say alpha. Alpha is always 5%. Can we all agree on this? Because 5% is what we agreed on with T-Lady. 5% is what all biostatisticians agreed is the cutoff. So it makes sense that our type 1 error is always going to be 5%. Clear? So here's what usually happens. We do a study, and for example, we got lucky, and we got this mean, and because we got this mean, we made the headlines on PubMed, and we gave them these ideas of how we can make students get better grades and stuff. We just said, oh, it's very simple. You just hook them up to an IV and water, and there you go. They're all going to get 100. Then someone in Germany or France or Saudi Arabia or people just repeat the study, and they say, hold on. We're all getting values here. So what did they then say? They say that this person that published this article, he actually had a type 1 error. And we'll see this in he likes using memes. These are memes back in his day, he has a really good meme that talks about this and how repeating a study, let's say you do a study 20 times, 19 times they'll be here. 1 time, on average, it'll be here. Does that mean that the water works? No, it doesn't mean it works. But we have to know that it's possible. So back again to the guy who's 60 feet tall. Is it possible to be 60 feet?
Yes.
Is it possible that although the water really does not make you smart, you end up seeing a test that tells you it really does make you smart?
Yes.
It's always possible. Is it likely? That's where you tell you no. It's not likely because 5% is, we agreed on it's not likely. Also, by the way, when I say likely or not likely, I know it sounds crazy, but 4% is unlikely. Okay, unlikely. 6% is likely, okay? So I know they're crazy and they're very close, but the reason I say this is because we agreed on a 5% cutoff. You know what? Even 4.9 is unlikely. 5.1 is likely. Because we agreed on a 5% cutoff. It's only when you become below that 5% we start saying, you know what? It's unlikely for you to get this result by purely chance alone. Therefore, you probably made. Therefore, we should reject the null hypothesis. Make sense?
Type 1 error, diamond 5%.
Type 1 error is always 5%. Always. Okay? We all understand this, right? And we didn't spend an hour trying to use the example, which is nice. Now let's use KitKat. Now, KitKat, we don't know the distribution. I'm going to show it to you now, but we usually, I mean, you could know if you plot it, but you can't know the relationship usually between the distribution of KitKat and the distribution of the normal population. You can't know it. But I'm going to show it to you now. So it's going to be this one. And most of you are going to know class that, okay, it really does work. So look. Okay, so this is the distribution for those who got KitKat and sample 2. Now obviously KitKat doesn't make you smart during the exams, otherwise we'd all be carrying KitKats in the exam. But for this example, just let's pretend it does. Let's pretend the reality is that it really does make you smart during the exam. Now, we don't have something called a type 1 error. We don't have it. Because the reality is that it does work. So the only thing that can happen, a certain amount of percentage of the time, you will get values here, which will be after this cutoff. And since you're assuming that the null hypothesis is true, you're assuming this population is coming from here. So you're taking a p-value as if it's here. Does it make sense? Okay. This is really important. Remember when we said p-value is the probability of getting a result given the null hypothesis is true? This distribution is so difficult because I already showed you the distribution. Forget this exists. Forget this distribution exists. We don't know the distribution, okay? All we know, look, I took 3 samples, okay? Oh, forget this. I took 1 sample and their mean was here. Their mean was here. So now what do we do? What do we do? We don't know if KitKat works or not. So we can't say we have to assume it works. We don't know. We don't know. I'm just telling you because at the end of the day, did we make an error or not? For this example, KitKat, was it significant or not significant? In this example, significant, correct? So we go back here. We put this point on this curve because what is p-value? It is the probability. Probability that you get a result such that the null hypothesis is true. What does it mean the null hypothesis is true? It means KitKat did not do anything. So this sample that I got, I pretend that KitKat did not do anything. When I pretend KitKat did not do anything, it means I'm assuming they come from this population. So what's the chance that I purely by luck get this value? If we calculate it, it ends up being something like, for example, 2%. What does this 2% mean? It's the probability of getting a value as extreme or more extreme, all of this, given that the null hypothesis is true, given that KitKat doesn't work and I got this purely by luck. Is 2% unlikely or likely?
Unlikely.
It's very unlikely. It's such a small percentage. It's less than 5%. You all agree with me, right?
Yeah.
So what's the more logical conclusion? KitKat actually works and we reject the null hypothesis.
Because it's 5%.
It's less than. We'll do it again. This is where the confusion begins.
So أنا معي significant ليش significant؟ إحنا ما نعرف distribution.
You don't know the distribution. You only know this mean. Okay, look. We took a mean. They all got 90. 90. What's the mean?
90.
90, right? You all agree, right? So it's this value, right? It's this value regardless of the distribution or what the distribution looks like. It's 90, right? Let's go back to the previous lecture. Z equals what? X bar minus mu over standard deviation. Z equals 90 minus 70 over 5 equals 20 over 5 equals 4. This will correspond to a p-value, let's say, just for the sake of clarity, 0.02. It will be significant, I assure you, it will be significant. You all understand why I used Z, and you all understand what this p-value means? It means, this is what this p-value means. Remember when we, just a quick break. Remember when I talked about T-Lady? It's the exact same. I don't know why you understood it when I talked about T-Lady, but you don't understand it. It's literally the exact same. We're having the same dilemma. When I talked about pizzas, then I showed you the steps. It's the exact same. There's no difference. It's just I'm using a different example. If you can only understand it using the T-Lady example, you don't really understand it. The only way you'll understand is by applying different examples. Okay? We got this value. We don't know their distribution. We got this value. So now what do we say? What's the chance that this is significant? What's the chance? What's the chance that this will be significant given that KitKat does not work? What's the chance that T-Lady gets it right given that she gets it by pure luck? She doesn't know how to get it. They're the exact same thing. T-Lady was 5%, KitKat was 2%. That's the only difference. That's the only difference. Does it make sense? To everyone. This is a really important principle. Everyone understood it. We'll redo it. Look, it's not fair to yourselves if you're not being honest. This is a really important principle. Who understood it? Just raise your hand. Who did not understand it fully? Just raise your hand. Okay, almost half the class is raising hand. It's not fair. It's not fair to you guys. We're gonna redo this. We're gonna redo this. Does water work? In reality, does water work? Okay, so here's what will usually happen 95% of the time. You will get a mean here, or here, or here, or here. In this example, we got it here, and this is 70. So what's the chance, what's the probability that you would get 70, or more than 70, assuming water does not work? What's the chance? 50%. Does 50% make sense?
Yes.
That's the p-value for this mean. Does this make sense?
Yes.
Is 50% more or less than 5%? Way more. So is 50% significant or not significant?
Not significant.
Not significant. Not significant, right? So we are making the correct decision. Our null hypothesis is accepted, and our reality tells us water does not work. This is 95% of the time this will happen. 5% of the time, you will get lucky by chance alone. Pure chance. You picked a sample with beans list students. The water didn't help them at all. They got 90, 90, and 90. They got 90, 90, and 90. Okay? So now, you see this whole distribution? They were here. They were here. They got this mean. They got this mean. 95% of the time, you will get a mean here. 5% of the time, you will get a mean here. You understand this, right? If I got a mean here, and this mean, let's say it got a p-value of 2%, is 2% more or less than 5%? So is it significant or not significant? Significant. So do we reject the null hypothesis?
Yes.
So if we reject it, that means we accept, we say that water works. Does it?
Yes.
We made an error. What type of error?
Alpha.
Type 1 error. You see, all of it is connected. Now with KitKat, it's the exact opposite. Most of the time, we know that KitKat works, right? KitKat works. So most of the time, you will get a mean that's here. Forget about the distribution. Most of the time, you will get a mean past this line. A few, look, I'm not giving you a number. This is really important because it fluctuates. I'm just saying most of the time, you get a mean that's here. A few of the times, you get a value that's here. Let's take what regularly happens. Let's say what regularly happens. You give them KitKat, they're average students. During the exam, they get all 90s. So your mean was 90, your mean was here. It corresponds to this point. Okay? So then you do p-value, you work out p-value using z and everything, and you find out it's 2%. So this, you say this point, the chance I got it, purely by luck, KitKat did not do anything, is 2%. So what's the more logical conclusion? KitKat did do something. So we reject the null hypothesis and we accept our hypothesis. And our hypothesis says that KitKat works. Does that make sense? This is what regularly happens. Unfortunately, some of the times we make a mistake. Maybe they're below average students, and once we give them KitKat, they got 70. So they did improve, but we don't know their previous mark. Instead, all we see is 70. Now, we work out p-value. What's the chance of getting a 70 or higher than 70, assuming the null hypothesis is true? What's the chance of getting all this?
50%.
Is 50 more than 5% or less than 5%? More. So to us, we see that KitKat did not work because we accept the null hypothesis. But does it? So they're contradicting each other. So it's a mistake, it's a type 2 error, it's a beta error. We're done with the lecture. Yalla, you can all go home now. The hardest concept. If you don't understand it, we can keep repeating it over and over again. But this is this lecture.
Did you read the
We're gonna repeat it so many times. Yani if your only concern is repeating, don't worry, it shouldn't be worried.
I didn't get the part about data.
But you understand alpha. All of you understand alpha, right? Alpha is easy because alpha is always fixed. It's always 5%. 95% of the time you will get the correct decision. 5% of the time you make a mistake. You all agree with me on this, right? Now I just want to add one last point to those who still understand what I'm saying. The reason it's more likely you get a point here is because KitKat actually does work. KitKat shifts the distribution ahead. KitKat makes you smarter, so you're more likely to get the value here. That's why the probability of KitKat working is not really 2%. It's not really 2%. But we assume it's 2% to find out what's the chance of us just getting lucky. You understand it? We are handicapping ourselves. We are saying that KitKat does not work because we want to know what's the chance that we got this value purely by luck. We don't want to see the distribution. We don't want to see that KitKat is actually affecting something. Instead, all we see this mean, we say, what's the chance we got it by luck? Is it less than 5%? That means it's significant. That means we reject the null hypothesis. We accept our hypothesis. Most of the time, this will agree with reality. A few of the times, you will accept the null hypothesis, but the drug actually works. This is a beta error. Some of the times, a few of the times, you will reject the null hypothesis. In other words, the drug really does work, but the reality says otherwise. And that's an alpha error. That's a little summary. We'll go over it again. But for now, the majority of you should understand it, right? Right?
Yes.
All of you. I don't mean all of you, saying it's the show of hands. How many people still didn't get it?
طب can I summarize it؟ وبتحكي لي الصح
والله
ولا؟
يلا.
That's type 2 error اللي هو reality says yes but the test says no.
Do you all agree with this?
The reality says yes but the test says no.
Yes.
طيب
That's true.
هلا احنا we got samples وطلع معنا انه هو 2% by the test.
Yes.
We consider that significant.
Do you all agree?
طيب
She's right. Just say yes, show some confidence. This isn't the exam, you're not going to be wrong. Just
okay. بس it's not actually 2%, it's more, but it's not significant.
no.
خلصت الدنيا؟
Now, are you all in this problem together? When I say it's not 2%, it's more, I mean the probability of getting the result is more. It's more. Because look, it's more. This distribution, this is not 2%, this is almost like 50%. So the probability of getting that result is 50%. But the probability of getting that result, assuming the null hypothesis is true, assuming KitKat does not work, is 2%. Yes.
So is it always going to be 2% for all the hypotheses?
No, my examples are 2%. But what,
depends on the example.
yeah, in the example I put 2%. But what you're looking for, to say whether it's significant or not significant, you're looking for is this percent, is this p-value less than 5% or is it more than 5%? That's what you're looking for. Still not clear, صح? Still not clear? Okay, we'll redo it. Fine. Because you need to understand this. If you don't understand this, the whole lecture you won't understand. Alright. I think the problem